This is Women's History Month, and the AWM actually volunteered earlier to speak. This will be a great talk on the history of. You've got a lot of people she's going to talk about in the talk, and she didn't even list my favorite mathematician, who is Emmy Noether, actually. So maybe I'll throw her into the mix too. I highly recommend this one. Should be a good one. Let me say something about the next homework. I think it's not going to be too difficult. The idea behind this homework is we're going to be spending the next little while proving the fundamental theorem of Galois theory. I haven't even told you what it is yet, but that's what we're going to do. And I think that some of these questions will sort of help you with the understanding. The first one is consider the field extension Q inside of QX, rational functions over X. Show that Q of X squared is a closed intermediate extension. So notice Q of X squared is some field in between there, right? It contains Q and it's certainly inside of Q of X. Show that that's a closed intermediate extension. You don't know what that means yet. But QX cubed, which is also intermediate, is not. Two kind of plays a sort of another theme of this problem is the prime number 2. Let K inside F be extensions fields with a degree of F over K equal 2. That's the easiest sort of non-trivial extension you can think of, right? Because if the degree of the extension is 1, you're just talking about the same field. Show that if the characteristic of the field's not 2 and the degree is 2, then F is Galois over K. We talked about the Galois group. It's the group of automorphisms that fix K. We will define Galois today. What it means is that the fixed field of that group of automorphisms is in fact the base field K. Give an example of a field extension of degree 2, necessarily with characteristic 2, with F not Galois over K, and give an example of a field extension of degree 2 with the characteristic 2, and F is Galois over K. So in characteristic 2, it's sort of like Wednesday on Mickey Mouse Club. It's anything can happen day. 3, if E is Galois over K and F is Galois over E, is it true? So we know that this is true for algebraic, right? If E is algebraic over K and F is algebraic over E, then it's true that F is algebraic over K. Is the same statement true for Galois? And this will mean more to you when I define what Galois is. Okay. Any questions? All right. Here we go. Back to the adventure. As I promised last time, I'm going to so we kind of built up this little chart last time. I'm going to try to fill this in again. We're going to fill in this chart here and talk about what all this means. Okay, so let me sort of reintroduce you to sort of the notation here. Our situation is we have that we have Q, and then we have so we're looking at the field Q, omega, and alpha. This is actually the smallest field in which you can find all 3 roots of x cubed minus 2, namely 2 to the 1/3, which is alpha, alpha omega, and alpha omega squared, which is alpha omega squared. Okay. Notice that the minimal polynomial for omega is omega was that primitive cube root 1, and this was its minimal polynomial. So we made something like we made this table to kind of help us out here. And we investigated, I picked a particular basis, which was 1 alpha squared omega alpha squared. I left it to you to convince yourself this is linearly independent. And we had these automorphisms. And I investigated, we filled this kind of in last time. Throw this all in here. Now I numbered these roots 1, 2, and 3. So those are the 3 roots. And we built these automorphisms based on what they did to the roots. I had the identity automorphism. And it probably shouldn't surprise you that the identity automorphism left everything alone. I had this other automorphism, and what I mean is here is I tried to build one, and we were successful, that swap these roots, alpha and alpha omega. That was one of the big things that we picked up on, is if you have any automorphism in the field, it must take a root of this irreducible polynomial over Q to another root. So I tried to swap these and leave this one alone, and I was successful. And we got this. This went to
So for what? Is it true that for any polynomial, roots map to roots for any?
if it's irreducible over base, right? Because I mean, let me give you an example. I mean, if you had a polynomial like this. Well, it's certainly true that what's true is it'll take a root of this polynomial to itself, right? But it can't swap these two out, right? Because no automorphism is going to take 1 to 2 to 1, right? But it will take this root from here to here. What we have is x cubed minus 2 is an irreducible polynomial over the rationals, right?
Okay.
Because all 3 roots are not in there, and it's only degree 3. And so what I attempted to do to build this is I said, well, I've got 3 roots to this polynomial, and I made this field from this polynomial, and since it's the smallest one that contains these roots. And I said, well, you know, we've got 3 roots. And so you pointed out last time, I believe, that the number of automorphisms can be at most 6, right? Because there's 6 possible permutations of these roots. We'll try to build all 6 of them, right? And so we found out that if we swap these 2 roots, we get this. I think omega was conjugated. And the last 2 in this column were alpha and omega alpha squared. Then I tried to do this one. And what I got here was 1 squared, omega squared, alpha. Oh, whoops. And this one was a fun one, because this one actually turned out to be complex conjugation. Right. So everything that was real was left alone. And everything here was conjugated. The last one we did last time was this one. What this did was this cycled. This one took this root here, this root here, and try to bring this one back. We were successful building this one too. Omega alpha. And this is omega squared alpha squared. And this should be omega squared alpha and alpha squared. And finally, the one I didn't do, which I challenge you to do, the last possible permutation here is the swapping out the three roots in the other order. And what I got for here was one omega squared alpha, omega alpha squared, omega alpha, omega squared alpha squared. Notice that all these automorphisms are distinct because no two columns are exactly the same, right? And notice there's a certain amount of symmetry, right? Now I want to pick out something else. I want to look at this table. So I've got two things going on. The group of automorphisms the Galois group synonymously is isomorphic to, you want to guess? Very good. That's a great guess. I mean, this is not correct. That's three. There's only two groups of order 6. How did you know this is S3? Well, there's a couple of ways to do it, right? First of all, I don't expect a group of automorphisms in general to be a billion anyway, right? It certainly can be, right? But I'm suspicious of it. But let me point out that these three are all of order 2, right? And in S3, you have 3 elements of order 2, but in Z6, you don't have that many elements of order 2, right? So there you go. And of course, you can actually also check that composing these two in the 2 different orders are different, for example. But I want to point out I want to look at this intermediate fields between versus subgroups of the Galois group. Now, let me tell you, one of the things that I think appeals to me as being easier is this. I don't know much, but I know that the subgroups of S3, there's only finitely many. Everybody agree with that? Because after all, it's group 4 to 6, there's only finitely many subgroups. Intermediate fields, I'm a little bit less clear on, right? Is it clear to you that there's only finitely many intermediate fields here? I don't think that's so clear, right? I can think of several. How about Q adjoined with omega, just omega? How about Q adjoined with alpha? How about Q adjoined with alpha squared? How about Q adjoined with alpha plus alpha squared plus alpha to the 4th plus omega cubed plus omega to the 5th? That's an intermediate field. Now, does that make it a little less clear that there's only finitely many of them? There's all kinds of it. How about Q adjoined with omega times alpha? Right? It seems like there could be a lot of them. There are only finitely many fields, which is not I don't think it's clear at all. Let me try to compare this. Let me start off this way. How many subgroups are there? Oh, that's 3 now. Oh, you missed stuff on the easy ones. So Jim steals the easy ones. There's E and S3. Fine. And there are other ones. There's E12. E13. E23. And so there's a subgroup order 1, order 6. There's 3 of them of order 2. And there's also a unique subgroup of order 3. Right? Now, for every one of these subgroups, I can get a corresponding group. In fact, let me kind of draw the lattice here, and I'm gonna do it in terms of notation that I've already got here. So let's do it this way. Okay, so I've got so of course the 1, 2 corresponds to this P12, where I just plopped out the roots 1 and 2, and 1, 3 corresponds to P13. So got this other group here. And then I've got all this. That's a really not nearly as good as Matt McCauley's pictures, but hey, it'll do for now, right? This is a picture of all the intermediate groups. Now, I claim that for every one of these groups in this little lattice here, I can make it correspond to a field. How do we do this? Correspond each of these to a field between Q and Q alpha omega. I'm not going to be super precise here, but I'm gonna try to get us all a feel for this. Any ideas on how to do this? I'm gonna use my page. What's it? Okay, it's gonna be something like that, actually. So what I want to do is for each subgroup, find field consisting of all elements of Q alpha omega fixed by that subgroup. So let's start. Let me make this easy. What is the subfield of this that's fixed by all automorphisms that are the identity? Everything. Okay, so corresponding to E on the bottom of my picture, I've got that. Okay, let me go all the way to the top. What is the subfield of this that are fixed by everything? That is true. In this case, it's Q. Certainly Q is fixed by everything, right? The big question that I have to ask myself, though, is there anything else that's fixed by Q? Or I'm sorry, my bad. Is there anything else that's fixed by all the automorphisms? And here I'm gonna be a little bit fast and loose, maybe a little bit imprecise because we'll improve this, but this will give you the idea. Let me ask you this. How about alpha itself? Is alpha fixed by everything? Certainly not, because if you look at any row, any one of these basis elements is messed up by some automorphism, right? Omega is fixed by these automorphisms here, but not these here, right? And if you stare at this long enough and do some computations, certainly this top field contains Q, but in fact, maybe you can convince yourself that it is in fact Q. In fact, the only things that are fixed by everything comes Q. How about this? What's fixed by the identity, well, that's everything, and this? Doesn't look like anything's fixed by it. Or is it? Can anybody tell me? Actually, maybe it'll be easier to do this one. Let's do phi 2, 3, the one in the middle here. We don't know these yet. How about this? How about phi 2, 3? Can anybody kind of give me a good guess as to what was fixed by the identity in this? That is correct. Q of alpha is fixed by this. Because actually, if you think about it for a minute, what did we figure out that phi of 2, 3 was? It was complex conjugation, right? So what should be fixed by this? It should be the largest real subfield, which is Q alpha. And maybe that'll kind of help us out a little bit. In fact, anybody want to guess what phi of 1, 3 is? What happens when we try to, it's a fixed field of this.
Is it Q or bigger alpha?
It is. Notice, by the way, that alpha is one of our roots of x cubed minus 2. This is another root. Right? Notice that conveniently this one shows up in the table. You want to take a guess, phi 1, 2 now, which is actually the hardest one. Good. This doesn't show up in the table because I wrote a different basis, right? But if you notice, if you look at phi 1, 2 of omega squared alpha, this is phi 1, 2 omega squared, phi 1, 2 alpha. Phi 1, 2 of omega squared is actually should be omega. Well, let me get it this way. Phi 1, 2 omega, phi 1, 2 omega, phi 1, 2 alpha. this should be omega squared times omega squared times omega alpha. And this is omega squared alpha. So notice P12 does indeed fix omega squared alpha. So it looks to me like the fixed field of this is this. What about this?
Q omega.
Oh, good. Very good. Notice if you look at these last two columns and the identity automorphism, notice that they fix omega. Right? Now, at this point, I don't think I've probably convinced you that those are all the intermediate fields. You might be, hey, Jim, can't there be more intermediate fields than what you've drawn? And is this precisely right? But I think this gives the idea, because this is basically, if you look at this chart long enough, these are actually fixed fields. Let me show you something else that's interesting about this correspondence. What's the index of the identity in here? In other words, what's the order of this group? 2, 2, 2, right? What's the index of these three groups in S3? They're all of index 3, right? 6 divided by 2. What is the index here? It should be 3, because this is group 4 of 3, and this is 2. Everybody agree with that? Now, look at what happens over here. What is right? What is the index of this in this? Well, actually, let's do it from here. What is the degree of this extension here from Q to here? Well, to get from Q to Q alpha, right? The degree of the extension is the degree of the minimal polynomial of alpha. 3. And these are all three roots of the same polynomial. These three fields right here are in fact isomorphic, because x cubed minus 2 has 3 roots, and these are adjoining each one of them separately. What's the degree of the extension to get from here to here? Well, my guess is it's got to be 2. And it's actually fairly easy to see that all you have to do, actually it's easiest to see from here to here, this is a real field. And to get all the way up here, you need to adjoin this alpha. The minimal polynomial of alpha is x squared plus x plus 1, which is irreducible over this, because you need those two complex conjugate roots. What is the degree of this extension here? It's 2. Right, because the minimal polynomial of omega is x squared plus x plus 1. So this is a degree 2 extension. And then you have to join alpha to get here. It's degree 3. Notice the diagram is exactly the same. There's some other weirdness. By the way, there's another sort of group theoretic, really. There's no time that's going by either. I guess the clock's probably right now. There's also another sort of group theoretic difference in some of these subgroups. Anybody tell me what it is? Look at the subgroups of order 2, subgroup of order 3. There's an important contrast between them. Anybody remember what it is? Normally, I don't like to put you on the spot and ask questions, but can anybody tell me?
The 3 are conjugate, so they're not normal. 1 is normal.
Right. Right. These 3 subgroups are not normal in this. This one is normal. There is a corresponding sort of difference in the fields here. It's a little bit more subtle to pick up on. Does anybody notice there's something that's different about these three fields as opposed to this one? That's structurally different. I don't mean that it's a different degree or anything. Does anybody know what it is? So here's one way to think of this. To get from here to here, your minimal polynomial, you would join the root of this polynomial, right? How many roots does polynomial have? It's got two roots. You just stuck on one of them, right? And you got the other root for free. You agree? So this polynomial degree 2, you got both roots in here. To get here, in fact, to get to any of these, you stuck on a root of x cubed minus 8, right? Do you have the other roots?
No.
No. And that's actually connected to the normality, right? Which is kind of interesting, right? This is what it means. These intermediate fields are, we're going to talk about this in a moment. These intermediate fields are not Galois over Q. This one is Galois over Q. And that's the contrast between the normal and the not normal. Okay. This example, I think if you keep it in your notes, basically illustrates a lot of the big pieces and broad strokes of Galois theory. You see the normality, you see the degrees of the extension, the correspondence between the intermediate subfields and the subgroups of the Galois group. And that is basically what the fundamental theorem of Galois theory is going to tell us. Okay. Any questions? Okay, so let me I'm going to give this kind of to you here. This time. Just okay. So examples. What is the Galois group of any field over itself? Well, let's see, shall we? This should be the group of automorphisms of F that fix F. There's only one of those, right? This is the identity. Multiplicative group 1. How about this one?
It's not the one that you just.
Yeah, it's not actually. This is the identity. The Galois group here is just the identity. This is a bit of a subtle point, but let's point this out. Let's think about what this one is. This is all automorphisms of Q radical that fixed Q. Okay. So let phi now, all I really need to know, if I want to understand how that automorphism works, because I know it takes every rational number to the rational number, all I really need to know is what does this thing do to cube root of 3? So this is determined by phi of the cube root of 2. And it can only be cube root of 2, omega cube root of 2, or omega squared cube root of 2. That's it, because our observation was any automorphism must take a root of that irreducible polynomial x cubed minus 2 to itself. But the answer is it can't be either of these, because these are not in cube root of 2. Because remember, it has to be an automorphism of this field. It has to put it inside its field. Your only option is to take the cube root of 2 to itself. Therefore, phi of the cube root of 2 is cube root of 2, and phi is the identity. So that was a little bit tricky. But it's an important example to keep in mind. Now, for the other one, the one where I had the S6 for the Galois group, well, that's because you can now take the cube root of 2 to any of the roots. You've got complete freedom now. Okay, how about this? Anybody want to venture a guess on that one? I'm really kind of appealing to intuition here. But anyone, yes.
Should be either only one element or two elements, because we, I don't know if we can push it's at least have two elements, because you know we can spread the curve.
What if I told you this Galois group had 4 elements? There's 4 elements. Does that help you?
Oh yes, because there is square root of 2 and square root of 2.
There you go.
Square root of 3 and minus square root of 3.
Right, so you've sort of got 2 different things going on. You got sort of 2 different irreducible
Yeah.
polynomials of q. You got x squared minus 2 and x squared minus 3. So the radical 2 can go to either of those 2 roots, radical 2 or negative radical 2, and the radical 3 can go to itself or minus radical 2. Does that give you a guess as to what the Galois group is?
Yeah.
No, Z2, Z2. Right, because every automorphism has, so the automorphism that takes radical 2 minus radical 2 has order 2, and the one that takes radical 3 to minus radical 3 has order 2 as well. Okay, I'm going to give you kind of a first theorem here that sort of puts down in general form what we did in that table a little bit. So without further ado, let K inside E inside F be fields. And H, a subgroup of the Galois group of F over K. Number A. I'm going to introduce this prime notation. H prime. This is the set of all V and F such that sigma V is equal to V for all V and H, or I'm sorry, for all sigma and H. Is an intermediate field. To the extension K inside F. So in other words, H prime lands somewhere between K and F. Notice H is a group, and this prime notation turns groups into fields, right? Because it is, in fact, H prime is a collection of elements of the field. And what's special about these elements of the field? They are fixed by everything in the subgroup H. As you might guess, I'm also going to prime intermediate fields. B. E prime. A field prime is going to be a group, and this is the set of sigma in the Galois group of F over K that fixes everything in E. Is a subgroup of the Galois group. Okay, so I left the proof in here as an exercise, but let me just sketch it out a little bit. Maybe not in complete detail, but I think it might help us get used to the notation. It might help me get used to the notation if we work through this a little bit. Hey, okay, H prime by definition is all the stuff in the field that's left alone by everything in H, and this needs to be an intermediate field. Let me note first that K. So let me just make sure that I've got all my ducks in a row and point out that certainly H prime is contained in F by its very definition. And since everything in the Galois group fixes K, then everything in K has to be in H because everything in K is automatic. So at least it's where I said it is, right? Now, what I need besides that is I need this to be a field, don't I? So notice that if V1 and V2 are in H prime, then sigma of V1 plus V2 is sigma V1 plus sigma V2, which is V1 plus V2. Sigma of V1 V2 is sigma V1 sigma V2, which is V1 V2. And let me just say at this point, right? I've got that it's closed under addition and multiplication, and right. How about the other B? We want to verify that E prime. This is a set of everything in the Galois group that fixes E is a subgroup, right? Well, so let me point out that so the identity is an E prime, so E prime is not empty. And so now I'll use the subgroup criteria. Suppose now. Sigma 1 and sigma 2 are in E prime. Right? Well, notice that sigma 2E equals E for all E and E. So E equals sigma 2 inverse E for all E and E. You gotta love automorphisms, right? I'll just take the inverse function over the other side. Now, hence, for all E and E, if you look at sigma 1, sigma 2 inverse of E, this is sigma 1, sigma 2 inverse E. Well, we already remarked above that this is E. And of course, sigma 1 is an E prime, so this is E as well. So therefore, sigma 1, sigma 2 inverse is in E prime. So we proved it's non-empty and satisfies the subgroup criteria. So that proof is really a little bit more complete. Okay, so let me make another couple of remarks here, and then I'll tell you, lucky you, exactly what it means for extension Galois. So here's some remarks. H prime is called the fixed field of H in F. Right, H is a subgroup of the Galois group, so H prime is a field. It's called the fixed field because it's the collection of elements that are fixed by that subgroup H of F. Notice that one prime, let's see. So if this is the identity group, this is a set of everything in the F such that the identity leaves it alone. So one prime is all of F. That is certainly true. However, the Galois group of F over K prime is not necessarily so the fixed field of the Galois group is not necessarily K. It might be bigger, right? So if you look at the entire Galois group, if you look at its prime, it's everything in the field that's fixed by everything in the Galois group. It is true that this contains K, but it might be bigger. So for a concrete example, if you look at the Galois group of Q, okay, we already know that this is just the identity automorphism, right? And we just do that example. So if we prime this, strictly things, right? Because the Galois group, the cube root of 2 over Q was the identity. So everything in Q radical, every automorphism that fixes Q also fixes the entire field. And so its prime is too big in a certain sense. So I will give you a final definition and send you on your way for the weekend. Hopefully the math up first. But definition 825. So here I'm going to tell you what it needs to be Galois. Like K and FB fields. We say F is Galois over K. Over K. If the fixed field the Galois group of F over K is precisely and let me point out, and this is a simple observation, but will prove useful later. Equivalently, F is Galois over K. F is Galois over K. Here, known as for all alpha that's in F minus K, there exists sigma in the Galois group of F over K such that sigma alpha is not equal to alpha. So that is to say, it's Galois over K if for every element in F that doesn't lie in K, there's some automorphism of that that moves it. This seems like a definition that I just made up for fun. However, Galois is incredibly important, even though probably on the surface of it, it doesn't look like why that would mean much, but it actually does. And we will talk more about this later. Any questions? Yes.
Is that an economic?
Yes. Yeah. Equivalently. Yeah. Other questions? All right. Well, you will have